So we have homework 3, which is due next Friday. And I'm going to have a quiz for you guys on stick diagrams on Friday as well next week. So I haven't put it here, but I'm going to have a little note here after this class. So next Friday, homework 3 is due, and also you're going to have a quiz that day. Remember the Xor Gate? What's the Xor logic? A not B or A B not, which is also the invert. If you invert the XNOR signal, you are getting XOR. So it's going to be A XNOR B invert, right? So that's XNOR as well. So what is this XNOR? A not, B not, or AB. So XOR can be either this or this. Now let's find out the Aoi logic for these two expressions separately. The first one, what does Aoi mean? And or invert. So you can simplify the logic. Instead of using gates, you can make the layout more compact, right? So Aoi logic and or invert. So everything has to be underneath the bar. Then you can apply the rules, which is if you have an OR logic underneath the bar, you are going to treat this guy as a NOR gate. So the PMOS are in series on the top and NMOSes are in parallel at the bottom. If you have something has an AND logic underneath the bar, then the two PMOSes are in parallel on the top and NMOSes are in series at the bottom. Does everyone know what I'm doing here? I mean, am I losing anybody? No? There? Kind of? Just remember this, memorize this for now. Okay? You know, this came from the NOR logic, right? A NOR B. Then the circuit looks like this. I've been doing this a million of times. All right, so PMOSes are on the top. Oh no, this is NAND, sorry. So NAND, if it's an AND logic underneath the bar, you have two PMOSes on the top in parallel and two NMOSes at the bottom in series. Right, remember that. If it's a NOR logic, then you have PMOSes on the top are in series and NMOSes at the bottom are in parallel. All right, memorize this for now for me, right? Just so you can understand the rest of the class. Okay. So now we have this logic, and it doesn't have a bar on the top, so you want to add a bar on top. Or if you don't do that, you just do whatever to follow the rules, and eventually you invert it, which works fine as well. You know what I mean? Just follow this rule. If you have an AND logic, then just have two PMOSes, because AND logic, two PMOSes on the top in parallel and two NMOSes at the bottom in series. And also for this one. But for these two blocks, it's a OR logic. So you want to have these two blocks in series for the PMOSes and in parallel for the NMOSes at the bottom. And then eventually invert it. So you don't have to get two bars on the top. Let's see. If I convert this guy to its Aoi logic, I start doing this. Start from this one, this gate. That's the unlogic. So I want to have two PMOSes. I start with the two PMOSes on the top first. For these two signals, do I want these two PMOSes in parallel or in series on the top for the PMOSes? No, that's the unlogic. Think about the NAND. They're in parallel, right? What are these two signals? A naught, B, for PMOS. Always think about this, the NAND gate and NOR gate. So it's unlogic, PMOSes are in parallel on the top. So unlogic, two PMOSes in parallel on the top. And then this logic, it's the same. Different signals, but the same logic, right? So I directly just draw these two PMOSes in parallel, but in series with these two guys at the bottom, because I know this is OR logic. So these two blocks should be in series for the PMOSes. Think about this NAND gate. They should be in series. This black box in series. So what are these two signals? What are these two signals? A and B naught. Do I want to short them together? Of course, because these two guys are in parallel. What does in parallel mean? That's in parallel, right? You have to close the loop. In parallel, need to short these two terminals together in parallel. So I'm just following all these rules and procedure to make it work. It's been verified. If you don't verify it, you can just apply all these possible combinations of the inputs into the gates, and you can verify it really quickly. Since you know it's going to work, you don't have to run the logic all the time, every time when you are designing a circuit, right? So it just takes a lot of time. Just remember this Aoi Logic procedure, how we are doing this. All right, it's going to simplify the design procedure for the future when you are designing the circuit. So now we are done for the PMOSes. You know, the PMOSes are pulling this output to VDD. So we are done with the VDD part. We're also one output for the truth table. Now let's do the NMOS. And we still want to start from here. So since this is unlogic, for NMOSes, these two inputs or these two NMOSes should be in series or parallel. Always think about this unlogic for the NAND gate. NMOSes are in series. What are these two signals? A not B. Does it matter if I have B on the top and A not at the bottom? Doesn't matter. But if you have this already set up in the schematic, in the layout, it matters. If you have A not, this signal on the top in the schematic, you have to do it first in the layout as well. But it doesn't matter for now when you are starting with the schematic. And then the other side, A, B not is unlogic. So think about this unlogic for the NAND gate. Two NMOSes should be in series. So what are these two signals? What is this? A. One question, should I short these two terminals as what I'm doing here? Should I short these two terminals or not? Why? If I short these two terminals, these two gates are in parallel. And these two are grounded, so it's shorted as well. So these two are in parallel, these two are in parallel. I want these two guys in series. So you're done here. However, this is not this logic yet, remember, because there's no bar on the top. It's being inverted. You have to invert it back. Why? Because all these Aoi logic circuits are inverted. If you have an unlogic, you just follow the rules, you find that this kind of circuit is actually A and B not. It's a NAND gate. It's being inverted. Why? Because when you are turn on these two NMOSes, you give a 1, give a logic high, you turn on these two NMOSes, but however, it's going to turn on this channel and pull the output to the ground. So you can see it's being inverted. Right? If you give a 1, or give 2 1s to these two NMOSes, you are getting you have 1 1 as inputs. However, the output is being pulled to the ground because these two NMOSes are pulling the output to the ground. So you are getting a 0. This is being inverted. It's an Aoi logic and or invert, right? It's being inverted. That's why when you are having a logic like this, when there's no bar on the top, it just follow the rules. It's not this logic. So whatever here is actually this thing bar. Why? Because if you do this, you can find out if you just separate this overall bar on the top, then what if you follow the rules, what you're getting is actually this bar. What is this logic? So I have to invert it again. So the output here will be A, X, or B, eventually. If you want to verify it really quickly, which is easy, right? You just have a truth table, A, B, A, X, or B, 0, 0, 0, 1, 1, 0, 1, 1. If it's 0, then 0, when they are different, you get a 1. Plug in all the A and B's in there and see if you are getting these results. You just verify all these input possibilities, combinations. If you get exactly the correct result in the truth table, then definitely this guy is a Xor gate. So that's when you just directly use this logic expression to find out the Aoi logic for the Xor gate. However, we also know that Xor is XNOR not. We have verified this for millions of times in logic. Still remember how to do that? De Morgan's law to do it for several times. So given that XNOR bar is XOR, then we can write this format, which looks pretty nice because we have a bar on the top and kind of logic at the bottom. So we can directly use the Aoi logic without inverted gain for the output of this complex logic gates. So how to convert it into the Aoi logic. This is also XNOR. This is also, so the entire thing here is also the same logic as this one. It's also XOR, right? But it's going to be a different circuit. See how that works. Start with these two signals. That's the unlogic, right? You need the two PMOSes on top. I start with the PMOSes. Start with the PMOSes, and these two signals are being shorted to the gates of the two PMOSes. And these two PMOSes should be in parallel in series. It's an AND or logic. AND, right? AND logic. You want to think about the non-logic here. So the two PMOSes are in parallel. So you're getting A naught, B naught in parallel. So that's in parallel. You want to close these two terminals at the same time, on the top and at the bottom as well. So if you compare here with this one, what's the difference? This is A naught and B in parallel on the top. This is A naught and B naught on the top in parallel, right? It's a different circuit. And then the next one, because you know these two black boxes are being ORed together on the top, So for these two black boxes, they should be in series overall, right? So you want to start drawing these two PMOSes below this guy. So you have A and B, these two signals. Should I close it or not? Yes, because they're in parallel. All right, done with the PMOSes. NMOSes, unlogic, in series, A naught, B naught, in series, AB, do I want to short it here? No, because they are in series. They should be in series. What's next? That's a perfect Aoi logic. Done. So that's the Xor gate. Where's the output? Here, here, here. Let me know. 1, 2, 3. Which one? Do you want to verify it? Let's see. Look at this true symbol. If we have A, B are both zeros, what's going to happen? A, B are both zeros. You're getting 1, 1 here. What you know, at least for now. You got two high voltages for the two PMOSes. It's going to block the pathway to the VDD. So definitely everything here is open circuit. Let's just look at here. A, B are both zeros. What's going to happen? 1, 1. That's open channel. So, boom, being pulled down to the ground. Works for the first one. Second one, 0, 1. 0, 1. You are expecting 1, right? So let's look at the PMOS first. 0 for A, so which means you'll have a 1 here. And 1 for B, you got a 1 here. 1 here. And 0 here. 0 here. So what's happening? What's the pathway to it? Yeah. It's being pulled to VDD in this way. All right, and then the third one, because A and B they're symmetric, right? So if 0, 1 works, then 1, 0 is going to work as well. How? A is 1, so here's 0. B is 0, so here's 0. So the pathway is this. Like this. So you can always pull the output to VDD. 1, 1, you're expecting 0. Let's first take a look at the PMOS, see if it's been blocked. 1, 1, 1, 1. It's getting cut. So these two PMOSes are off, right? So there's no way to VDD. But you have 1, 1, these two NMOSes are on, it's being pulled to the ground in this pathway. What about these two? They are off. Does that matter? Nope, because you have a pathway to pull it down to the ground. So if we do not use Aoi logic, if we just use the gate level circuits, just follow this logic. You have A, B, so you want to invert A, and you want to invert B, you got a B naught. So it's going to be A naught B go through an AND gate, and AB naught go through an AND gate, and then OR them, they can get A, X, or B, right? That's the traditional way to do it. You can imagine, I mean, I don't want to do it again, but if I follow this one, just draw all the gates. So that's the layout. Are getting this? I mean, what are these two? What is this? There are two crosses, a little bar in the middle. What is this? That's a PMOS, that's NMOS. Where's the channel? Yeah, the bar between the channel, right? So here's the channel. That's a PMOS, so this is a P plus. Here's a P plus. What is this material? Polysilicon. What's the color in electric VLSI? Pink. Yeah. That's a gate, right? And that's a channel. P plus. That's a PMOS. And just follow the gate level circuit, you're getting this. If you use whatever I do here, you're getting this. How? Let's take a look at it, how I do that. Let's start from the top. Since we have 4 PMOSes on the top, 1, 2, 3, 4. And 2 are in parallel, so these are the gates, right? This input signal. 2 in parallel and then in series with another parallel PMOSes. There might be multiple ways to do it, but let me just do whatever I have done here. Guarantee it works. If I draw a VDD signal from in the middle, like this, then I immediately got 2 PMOSes in parallel. Which 2? Left and right. Because the signal current is being drawn from the VDD, from the power supply, and reaches this P plus, and there are 2 branches, one on the left, one on the right. So it's gonna flow like in this way, and runs through these 2 gates, so which means that these 2 PMOSes are in parallel. And after that, so the VDD current being split into 2 branches and merges in one point. So after these 2 currents runs through these 2 PMOSes, it has to be merged in one place. How do we want to do that? Short it, right? So I'm done with this part. What's next? You want to treat this signal line, because this is a wire, right? It's can be considered as one point in the circuit. Metal, same potential everywhere. Doesn't matter, it's a wire, it's a piece of P plus, doesn't matter. As long as it's being shorted together, it's considered as one point. You can merge all these points together. Just think about that. You are melting this metal wire and you merge these 2 points together. It's not changing the circuit, right? So this is just one point. This is a wire, but actually it's just one point. And after this current is being split into 2 branches and reaches this one point, and reaches this one point, it's being split again in 2 branches to flow through 2 other PMOSes. So that's one point. It's naturally actually just going through these 2 PMOSes, because there's no other places to go, right? So it's going to flow like this and flow like this. I mean the current, it's going to flow in these 2 ways. You can imagine these 2 points is one point. And the current is going to be split into 2 branches and flow left and right in these two directions for these 2 PMOSes. And eventually reaches here, and eventually reaches here. And according to the schematic, this place is also one point. So how can I implement it here in the layout? Split split, merge. What's this material? What is this wire? What's the material here? What's being shorted to P plus to make the connections for the P plus and N plus for the drains and sources? What's the material to make all the connections? Metal 1. Because the substrate is at the bottom, at P plus. So what's happening here is it has a via and has a metal 1. Metal 3 is on the top to connect to all the bonding, the frame pads for the chip, right? Metal 1 is at the bottom, being directly shorted to P plus. And we're going to take, get into the details of the layers starting from next week. So no worries. So these are metal 1 wires. And after I short these two P pluses together, am I done with this PMOS on the top? The PMOS is on the top. Yeah, done. That's everything for these circuits. And for NMOSes, it's even easier because these NMOSes are just in series. You just need to introduce one wire, then it's going to go through from the drain to source, source to drain, like that. So I just need 4 NMOSes at the bottom. 1, 2, 3, 4, 5. 1, 2, 3, 4. So I have 5. You have 5 N pluses, but 4 NMOSes. Why can I say this circuit has 4 NMOSes? Yep, but what's the indicator? So when you are trying to count how many transistors you have in the circuit, you are looking at what? The gates. Since whenever the current flows through a gate, it flows through a channel. One channel means there's one transistor, because that transistor is being controlled by the gate. That's one transistor, it's like a switch. So how many transistors I have in this circuit? 4. 1, 2, 3, 4. 4 gates. Like 4 hats, right? You're asking someone to come to home for a party. You're counting for hats. How many hats? 4. All right. Where is the output from the PMOS? There? Yeah. Then you want to introduce this wire to the NMOS. So where do you want to start with? I mean, you want to connect this one to where? Which is the best way to do it? Yeah, center. Because it's being split into 2 branches. The currents are flowing left and right, and directly go through these 2 NMOSes, which is in series, and then short them to the ground. Short them to the ground. Short them to the ground in series. In some of the design, if you're not using the gate to turn on and off, so it's always on, then in these cases, you don't even need the gate to be there. It's going to have the same effect, which means if you have a circuit like this, 2 NMOSes in series, these are the vias, and you have a metal to connect these 2 together, and here's another metal one to the other circuits. That's in, that's out. And for example, the width to length ratio is W over L, W over L. Okay, and how many L's, how many width? I mean, if you want to draw equivalent circuit from this guy. The current is flowing. So here's the channel, right? The current is flowing like this. If you want to combine these two nodes together, because these two nodes are being shorted by a metal one, so it's just one voltage node. If you have, so these two NMOSes are series, right? So it's equivalent to this schematic. This is W over L, W over L. So what's the equivalent circuit for these two NMOSes in series? It's just one width here, but two L's. This is longer. The current is running into a longer channel. The width is not being changed. So what's happening here is you can directly draw one transistor, but with the W over 2L, and you are getting the same current. It's contributing the same resistance, same current, same driving capacity to the circuit. However, it's not able to pass NCC because I have two devices here, but only one device here. They're not passing NCC, right? That's the only downside of it. But it is able to simplify the circuit a little bit. For here, can you ignore some of the gates, just not drawing it? No, because you have to connect the signal to all the gates, to every single gate of each transistor that are being used. You need to introduce a signal to each transistor. And now let's take a look at this layout to label all the A's and B's, see if the order matters. Most of them do not, but some of them, like this one, the order matters. So let's start from the top. And VDD is being introduced from the top and being split into two directions. So definitely you know these two gates need to be shorted to A0 and B0 respectively, right? So which ones should be A0, which one should be B0? Two branches, A0, B0 or A0, B0. Doesn't matter. Yep. It's the magic. Then merged into one point, then being split again. Then you have A and B should be introduced to the PMOSes. Now, doesn't matter which one's A, which one's B. One more time. So which means if you connect A here, connect B here, doesn't matter. It's still some magic, doesn't matter. You have one voltage node, it's still just one wire. You know, you can do whatever you want. They're in parallel. Let's just label this as A and this as B. And merged at this point. And merged at this point. Now, being split into two branches. Two branches. So it should be A0, B0 in one direction and AB in the other direction. And it doesn't matter, right? Since they are in parallel. However, you cannot label this guy as B0. So you can put A0, B0 here and A, B here, right? Because A0, B0, A0, B0 in series, AB in series. However, you cannot swap these two signals. Is that making sense? The order here matters. If you do not connect these two signals to these gates in the correct position, then you cannot pass NCC. However, for these ones, for these in parallel, these parallel ones, it doesn't matter. Here matters. Just want to make connections. A0 should be shorted to A0. So imagine you are laying out this circuit in electric VLSI, Can you make this connection directly using the polysilicon layer? Are you shorting any circuits? If you directly draw polysilicon and the pink color thing and short these two signals together, are you going to short any circuits? No, because these are metal ones. This is poly. They are in different layers. However, if you have a really long, the reel-to-reel distance is really long, but by some reason, I don't know, just design it in that way. Can you still draw a super long polysilicon wire? It's not ideal. Unless you have to, right? So if you have a really long distance, you want to connect these two gates together. It's a one signal line. What you want to do is, whenever you get a space, you just convert it into a metal, which means you just drill a hole to the top layer and run the traces on metal one, and then drill a hole as a destination when it's closer to this gate, and drill a hole downward and get a poly connect to this destination. You just don't want to run polysilicon everywhere. Why? Has a resistance. It's not a perfect conductor. Don't use it wherever you want, right? You just want to use metals if you can. If it's not super long, which is fine. Okay, I just don't want to see in your layout you have super long polysilicon layer wires everywhere. Just use it as a metal. Then I'm going to take points off. Keep in mind. So the polysilicon cannot be super long. You want to convert into the metal layer and then run the traces and then come back to the silicon, which is here. I'm going to drill a hole to the top and run the traces and come back to the polysilicon, connect to the gates. What about these two? Have to think about it, right? Why? If you introduce a polysilicon, it's going to short with this poly. Even though it's not, I know it's not a huge circuit, so if you directly use a polysilicon, it's fine because it's not really long, far away from here to here. Okay. But now think about that. You have metal one layer here, you have a polysilicon layer here, and you want to short these two gates together since they're using the same signal. It should be one wire. How do you want to do that? You can do metal 2. Yep. What is this? Metal 1. This is metal 1 as well, right? So it is safe to do this. No problem, because this is metal 1, this is poly. You can put it here, and then drill a hole to metal 1, and drill another hole to metal 2. So use metal 2, come to here, and then come back to metal 1 to poly, then do the connection. It's not a unique way to do it. There must be another way to do it. But I think this is what I can think of right now. B knot. You have a B knot here. You have a B knot here as well. It's also B knot. Wait, B knot. B knot is here. Sorry, it's a gate. Whatever. I mean, whatever you want to do. Right. Just poly. Or you can drill a hole, get into metal 1, and make the connection. B. Oh, that's easy. Poly. Done, right? Then you still have to think about the signals. How can you introduce the signal to the left-hand side? So you're supposed to do this, right? So these 4 signals are A knot, B knot, A, B, because they are going to use this. You want to export all these ports. So all these connections need to be shorted to, so A knot, I mean, I'm ignoring the layers. So whatever layer you want to use, just do not short it, right? So the goal is you need to have all the signals available on the left-hand side. Okay. So when you are using the entire block as a module in the library, you just want to directly drop it off in the layout view, reuse it in the future for the upper layer circuit. So you want to have all these signals available. You just don't want to have all these signals inside the circuit. So whenever you are connecting all the signals to whatever inside, you still have to consider about the metal 1, metal 2 poly layers, not shorting all these wires, right? You just have all these pins available on the left. You're similar to use the gate, right? Like this. You have signals here and output here. Just convenient. Here's output. And you want to export this output as well. Okay, that's the Xor Gate. It's a lot smaller than the traditional one. And I have more examples for you guys. Let's take a look at it. So what about this? Nut. What's the first step? Two bars. Invert, invert. It's not changing the result. And then you use the De Morgan's law for this part. So it is split the bar, change the sign. You're getting this. Bar on top. So this is A or B or C or D naught. What is this? Four input NOR gate. Right? The signals are A, B, C, D naught. That's a schematic. What about the layout? Stick diagram. Before you start laying out anything in electric VLSI, do the stick diagram first. How many PMOS is on the top? That's pretty easy, right? Just 4 PMOS in series on the top. One, two, three, 4. Is that difficult to run 4 PMOS in series? It's very simple, right? Just boom, boom, done. And 4 NMOS is at the bottom in parallel. 1, 2, 3, 4 in parallel. How? This two? So let's think about it. If I, for example, if I short this signal to the middle part here, then I got 2 in parallel So what I did here is I introduced a signal here and one here, one here. And you'll let me know what's next to finish up this guy. Yeah. Why? So signals are being introduced from this one node. It's being split into 1, 2, 3, 4. So 4 NMOSes are in parallel. And that signal, that output is merged into this node, which is ground. So this is how you can make these 4 NMOSes in parallel. Just by simply drawing these PMOSes in series, looks like, but eventually they're in parallel. It's very compact. Save a lot of space on the chip. I know you need more practice, right? So that's why I have homework 3 for you guys due next Friday. And I know you'll need a quiz, so that's why next Friday you have a quiz. We are turning in homework 3. Right? Just run some examples. Probably repeat all the examples I demonstrate in the class. Will be good enough. Plus the homework assignment. Should prepare you really well for the quiz, I think. Next. Y equals to A or B or C. How about this? Great, I have a bar on top, so I can directly use the Aoi logic without inverting eventually. And I have these two blocks. So the D signal and whatever here in here is the AND logic. So I'm going to have, for the PMOS part, these two should be in parallel. So I'm going to have a D signal here and have whatever here on the right hand side. Since this is an OR logic, so they should be in series. Done for the PMOS. A, B, C, D. Doesn't matter which is A, which is B, which is C. Nope. Not for now. I'm done for the PMOS. Now the NMOS. These two parts is AND logic being connected by this AND logic. So D and whatever here. So actually D and here, these two should be in series, right? And the OR logic here should be parallel, in parallel. So you can imagine it's going to be a NMOS has a signal for D in series with these 3 signals, which are ABC. So that's the circuit Aoi logic for this logic expression. And how to lay it out? Look at the PMOS first. I have 4 PMOSes. One, two, three, 4. 3 PMOSes in series and 1 PMOS in parallel with this series PMOSes. That's not difficult, right? It's just So what I did is it's not a unique way to do it, but what I'm going to do is I will just introduce the 2 VD from the top to these two sides. So the signal comes to this P plus, it's going to flow through these 3 NMOSes and reach here. So these 3 PMOSes are in series, and VDD from here and this single NMOS, which is signal D. So that's the point which they got together. So that's the output. Now let's look at the NMOS. 1, 2, 3, 4, 5. 1, 2, 3, 4. Because this is the output, and this output has to run through 1 NMOS first, and then 3 NMOSes in parallel. It's a little bit tricky. Let me show you what I did here. So I connect it to here first, and then here. Then what? So this signal comes down to the NMOS. So the signal is going to run through this NMOS first, and this NMOS are merged here because I have 3 NMOSes in parallel. So it's going to run through this NMOS as well, and I want to merge these 2 nodes. So I got this so here's a question. Does it matter I have D on the top and these 3 parallel NMOSes at the bottom, or I can flip them? So which means I can have these 3 NMOSes on the top, and then I connect the D signal at the bottom. Can I replace this guy with this guy to implement this logic? Yes, so there's no difference. If you want to use this one, you have to make the layout like this. You know what I mean? Because the signal comes down here, it's going to meet with these 3 parallel NMOSes first. See here? 1, 2, 3, and merge. So the merged signal is being sent to this single NMOS at the bottom, which is this guy, and ground. So what's this signal? What's the signal for this gate? D. Doesn't matter for these 3 signals. In parallel, doesn't matter. So you can label A, B, C, doesn't matter. Depends on all the signals on the top, right? So which way is easier to assign in that way. Now label the signal for the PMOSes. Signal being introduced from the VDD, and there will be 3 PMOSes. So A, B, C, right? Since I have A here, so I'll just label A here. B, C, make it easier. Have to change the signals here as well accordingly. It's confusing you. Let's don't do that. A, B, C, and D. So poly C, A, B. That's how to do this circuit for this logic. All right, we'll see you on Friday. We'll run more examples.